as we all know, one of the things that we really enjoy working with over here at Google are very large data sets, very complex problems, lots and lots of bits coming through. And nowhere is that more true than in the astronomy world, where each night on a telescope run we have terabytes and gigabytes of data coming through, and all that has to be sorted, the signal to noise ratio adjusted and processed. So it's a really large and complex issue, and that's why we really enjoy working with our friends at NASA and throughout the astronomy community. And so today we're very pleased to be joined by our friends from the Keck Observatory down in sunny Hawaii. So I can definitely say aloha to that. I was really pleased to get my lay today. I've never been to Hawaii, but now I really have to go even more seriously than before. So we're pleased to be joined by Dr. Taft Armandroff. He is the director of the observatory, and he's going to talk to us today about some of the new innovations that are going on at Keck, and how we work with those large data sets and really just make astronomy even more accessible to the general public. So just want to give you some quick background on Taft as well. So he graduated from Wesleyan and earned his graduate work in Yale, all in astronomy, of course. And he's authored over 41 referred journals and review papers. And his research areas not only focus on managing these large, massive telescopes from Arizona to Hawaii and beyond, but more specifically in dwarf spheroidal galaxies, stellar proportions in the Milky Way galaxy and nearby galaxies, as well as globular clusters, the chemical evolution of galaxies, and dark matter. And so he joined Keck in 2006, and he will be very pleased to show us the latest innovations. We'll have time for Q&A at the end, and I'll have a mic. So without further ado, please join me in welcoming Taft. Thank you very much.
Thank you very much, Cliff. It's an honor to be here at Google today, and there's so much we have in common here at the center of the information revolution. Cliff did a great job talking about the complex data sets and algorithms that I think both of our organizations are really interested in. Information is an absolute key in astronomy, and just as a small sample of what we have in common, we're all thrilled with Google Sky, for example, and that's a real tool both for our community and for the general public in learning more about the universe. So let me begin by telling you a little bit about the observatory. These are our two telescopes opening up for another night of fabulous discoveries atop Mauna Kea in Hawaii. These are the two largest optical infrared telescopes that are steerable, that can point to different places in the sky that are in operation today. So 10 meters. 400 inches across the primary mirror. Before they came online, the largest telescope was the venerable 5-meter or 200-inch telescope at Mount Palomar. We have a very advanced suite of instrumentation that sits behind the telescopes that produces the data. And we have an incredible site atop Mauna Kea here. It's a dormant volcano, of course, 14,000 feet elevation. So only 60% of the atmosphere is above us. At 14,000 feet, 40% of the atmosphere is below us. So that's that much less light to interfere with the observations. Astronomers love data, so we've surveyed just about every mountaintop on Earth that could be good for astronomy, and Mauna Kea has come out as #1. The reasons for that are several, but let me cite the two most important. One, the sky is incredibly dark in Hawaii Island. We're mostly surrounded by ocean. We have a rural economy. Population is very low. We have very progressive lighting ordinances that keep the light focused on the ground instead of shooting up into the sky. So we are working on incredibly faint objects, and we cannot detect them against a bright background, of course. So that's one. The other is that the air is just very stable above Mauna Kea. The air has been traveling across the Pacific without running into other mountain ranges or very heated up areas and causing it to become turbulent. So it's a very smooth shaped volcano, so we get a smooth laminar flow of air. And that's the area that Mauna Kea is absolutely exceptional of. It's the mountain that has the lowest level of turbulence in the atmosphere above it on Earth. Here's a view of our telescopes. This is the primary mirror. This is the collecting area for photons coming in from the universe. So you can think of it this way. Imagine you were a photon that had traveled from a galaxy for 10 billion years. This is the view you'd see before you gave yourself up for the benefit of science. You can see we do everything we can to give a clear path to the primary mirror, and the primary isn't monolithic. The traditional way to make telescopes was to make one very large mirror. There's probably an analogy to computers here for all you Googlers. So the tradition was you make one very large mirror, and you have to make it thick enough so that it's stable against gravity as you point it at different places in the sky. Well, you can only scale that so far because of the thermal stresses. When you cast the mirror, they would crack as you made them larger and larger. So the project scientist for the observatory, when it was just getting underway, Jerry Nelson, came up with this concept that you could have 32 segments instead, 32 hexagonal segments, and each of them would have its own active control. So the backs of them have a lot of, and the sides have a lot of sensors on them. They feed their positions back to computers, and they're controlled very accurately. We have to keep the surface of this mirror within form to a 20th of the wavelength of light that we detect. So the shortest wavelengths of light that we detect at the observatory are about 1/3 of a micron. So we have to keep that surface within spec to a 60th of a micron. So it's pretty incredible technology, and it wouldn't be possible without distributed computers and sensors, which didn't really exist before the observatory came online in 1993. So you can see a person there to give you a sense of scale. So the light is collected by this primary mirror. It's reflected back up to the secondary mirror and concentrated, and then it bounces off the tertiary mirror right there into one of the instruments. The telescope is used for all areas of astronomy. I'll give you a sampling of some of the science that we're working on today, just a small sampling, but we've studied everything from the moon, if you can believe it, to the farthest edges of the universe, 13 billion, where light has been traveling from 13 billion years today, and in the sense that we're kind of cosmic archaeologists studying galaxies as they existed long, long ago. This is another view of the telescope, so you can again see the primary and the tertiary, but this is where the information is produced. It's produced at the instruments. And this is our DEIMOS spectrograph. It can produce spectra of about 1,000 objects at once. It's the most powerful optical multi-object spectrograph on the planet today. It's about the size of a small car, and it costs about $10 million and takes a number of years to develop, maybe 3 to 5 years to develop one of these things from concept to being implemented. So what's our mission? What do we do at the observatory? How do we grade ourselves? We have a broad mission, world leadership in ground-based astronomy, and what we specialize in are the following technical areas. One of them is high angular resolution astrophysics. That's getting the finest spatial detail we can get on the sky. As your telescopes get larger and larger, once you correct for the effects of the atmosphere, you get finer and finer spatial detail, higher angular resolution. We do a lot of spectroscopy of the light, and so that's going beyond imaging and getting, of course, the energy distribution as a function of wavelength for every object that we study. And you just need to collect a lot of light to be able to slice and dice it into spectra. So having the world's largest telescope is very enabling in that. And we do spectra on faint objects, we do very high precision spectroscopy on brighter objects, and we do highly multiplex spectroscopy. So being able to get spectra of between 10 and 1,000 objects in a given field of view. We're a fairly small organization and a fairly young organization, so one of our missions is to exploit emerging opportunities. That ranges from time scales of during the night. If we find out that something really exciting has happened that night, like a gamma ray burst has gone off somewhere in the universe and has been detected by a satellite, we need to have the flexibility to get on that and understand it. But more broadly, we have to be very flexible to emerging trends in astronomy. Because of our size, because we're not a big federal or international bureaucracy, we can kind of turn ourselves around to these problems and be much more flexible. And we're all about training the future leaders in the field. We're very, as you'll see in the next slide, we're very closely associated with a number of universities, and we have a lot of students and postdocs deeply involved in our research and becoming the next generation of leaders. This is our metric, how we judge ourselves. I imagine you have a number of metrics at Google, but our metric is publications in top refereed journals per year. So we first started publishing scientific results in 1996, and you can see we're on a nice upslope in terms of the number of scientific results we publish each year. The productivity of the telescopes keeps increasing. We also measure by citations, of course, by how influential each paper is. And so we lead the world in terms of ground-based observatories, both in the number of papers published per telescope and in the impact of our research, the numbers of citations. So our partners are very important to us. Caltech and the University of California are our founding partners. I don't know if we have any UC or Caltech alums in the crowd today, but each of them control 36.5% each of the observing time in the telescope. So they each have 36.5% of the opportunities to carry out experiments in the telescope. NASA is a 1/6 partner and receives 14.5% of the observing time. And the University of Hawaii, while not a financial partner, they provide us access to this very special site on top of Mauna Kea and thus gain access to 12.5%. Private philanthropy is a major partner of us. The Keck Foundation gave us the capital, most of the capital to build the observatory to start with, and private philanthropy supports about 56% of our new development, our building of new instruments and what we'll talk about as adaptive optic systems. And this gives us some freedom from the government development cycle that can be a little slow. So let me go from the budget of the observatory to the mass budget of the universe, just to give you a sense of what we're learning about the universe and how quickly we're learning things, and perhaps how ignorant we were until very recently. One of the top results in the observatory's history was the discovery of dark energy by using distant supernovae as standard candles and beacons. The universe, we all know, is expanding after the Big Bang, and astronomers were using supernovae, so exploding stars, with Keck Observatory, and there are two groups. One out of the Australian National University, led by Brian Schmidt. They had a number of University of California colleagues, and another led by Saul Perlmutter. And what they were both trying to do with Keck Observatory and these distant supernovae is the peak brightness of type 1a supernovae had been calibrated so that they could be a standard candle. So if you could find a type 1a supernovae anywhere in the universe and you could get its spectrum, you would know what its absolute brightness is. So you measure its brightness with the telescope, and between the two of those, that gives you the distance. You also know its redshift, and going way back to Edwin Hubble, the further an object is away, the higher the redshift. It's much like in an expanding universe, you can go to the analogy of raisins in a loaf of raisin bread as the yeast is causing it to rise. And if you're on any one raisin, you see all the other raisins moving away from you. And the further a raisin is from you, the faster its expansion is seen to be, because the total amount of dough along that line of sight is larger, so the expansion is larger. So there's a linear relation between distance and redshift. Now, and that's all left over from the Big Bang and the exploding expansion of the universe. So what these groups were trying to do was to see if they could see the deceleration in this expansion as all the galaxies in the universe feel their collective gravity. That should, if it's strong enough, it should appreciably slow down this expansion. Well, the shocking result that came out of this was that they were seeing an acceleration in the expansion instead of a deceleration. So something was driving this acceleration. The universe wasn't slowing down, the expansion was speeding up. This goes back to Einstein. This result was the 1998 Science Magazine Results of the Year, which is very rare for astronomy to be the Science Magazine Results of the Year to start with. But we were particularly thrilled to have a result where the Keck telescopes had played such an important role. And Einstein, of course, had a term that he eventually dismissed in his equations for the behavior of the universe. It was the cosmological constant that showed a constant acceleration term. So this has become dark energy, and it's become one of the top problems in theoretical physics today and in high energy physics, to find the source of this dark energy that's creating the accelerating expansion of the universe. So the mass budget of the universe now, the best estimate is it's 73% dark energy, 23% dark matter, 3.6%, as you see, intergalactic gas that hasn't condensed into galaxies or stars, and only 0.4% stars and planets and us. So you don't feel terribly significant in this pie diagram, and it shows how much we have to learn about the universe still, and how we're very much on the frontier about knowing what our universe is made of. So what are we working on this year? I went through all of the programs we're working on this year to just find a few that are representative of what's the cutting edge in astronomy today. Oops, looks like I did something there. We're back. So one is, what are the internal structures of planets having Earth mass to Saturn mass caused by the various mixtures of rock, water, ice, hydrogen, and helium gas? So we're now able, as I'll say a little bit more about, to explore extrasolar planets to get beyond our own solar system in terms of studying planets. And we're really, the question originally was, are there planets around other stars? That's a really challenging technical problem that has now been solved. But now, in the last 15 years, this field has just exploded. And we're talking about, investigating with the telescope, what really makes the internal structures of planets different when planetary systems form. So I find that amazing. The second question that's getting a lot of attention this year is, how do galaxies lose their interstellar medium and transition from star-forming galaxies to galaxies that aren't forming stars? We call them quiescent. So a galaxy is born with a lot of gas over its lifetime. It turns a lot of it into stars, but galaxies lose their gas for various reasons and stop forming stars. What are the dominant physical processes that control this? The third question that I picked out is, do the fundamental physics constants, you all remember the various constants from your physics classes in college or high school, do they vary over the lifetime of the universe? And some clever astronomers have found a way to look at the spectra of quasars and look at and determine whether the fine structure constants that we use all the time in atomic physics, whether those constants are truly constant, or whether the word constant is a misnomer. So it's a very exciting brew of science questions that we get to look at each year. Let me spend a little time on exoplanets, because this is an area that's just changed immensely over the last decade. But I want to go way back. I want to go back to the late 1500s and quote Giordano Bruno, who was a monk in that era, and said, "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. We see only the suns because they are the largest bodies and are luminous, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no worse and no less inhabited than our Earth." And he really set the stage for what we're doing today, but he did it based on pure thought. He was completely right. There are planets around other suns, and we can't see them because they're not emitting very much energy, and they're so small compared to the stars that they don't reflect much energy as seen from Earth. I mean, they can easily be 1 million to 10 million times fainter than the stars. So the best analogy is like trying to see a firefly just outside of a searchlight as you're looking into the searchlight. So he came up with this from pure thought, but astronomers have been trying ever since to find extrasolar planets. In that era, astronomy was a high-risk profession. He was put to death and tortured for these thoughts, if you can believe it. They seem very innocent today, and it turns out that they were true. But challenging the dogma at the time was not encouraged. So what have we learned since Bruno wrote those words? When I was in graduate school, no planets had been detected around other stars. We only knew the planets in our own solar system, and we can debate about whether Pluto's a planet or not, but certainly it's not a very rich data stream to only know about the planets in our own solar system. So astronomers have been working very hard to find planets around other stars, and Keck Observatory has played a really big role in this. And the first way that planets has been found in the dominant way, the first planets were found, about a dozen years ago around other stars. And the way that it's done primarily is as a planet goes around a star, the star doesn't just sit absolutely constant in space. Going back to Physics 101 again, for every action there's an equal and opposite reaction. So say as Jupiter goes around our sun in a very long arc, the sun doesn't stay precisely still, of course. The sun is doing a little minuet compared to Jupiter's long arc. It does a very small orbit. And the characteristic size of its orbit is very similar to the diameter of the sun. So it's just, as Jupiter goes from one side around, it's just doing this little arc that goes around the barycenter of the system, the center of mass of the Sun-Jupiter system. So if we were looking at our sun from another star, as Jupiter does this arc, we'd see very small velocity changes in the sun's radial velocity, the velocity along the line of sight. Conversely, we can look at other stars and monitor their velocity. If their velocity is dead constant, they probably don't have planets around them. But if we see periodic motions in their velocities, it means that a planet is orbiting around that star, and that its gravitational influence has caused the star to do a small orbit. So this is an example of this kind of data. The velocities that you have to be able to measure for this are measured in meters per second. So you can walk a few meters per second. So we're able with Keck Observatory to measure velocities to 1 meter per second on stars that are typically 20 or 30 light years away. We have a very complex, very high dispersion spectrograph called high-res that takes the light of a nearby star, it divides it extremely finely, and it gets the spectrum of the star. And then we can cross-correlate that spectrum to determine the Doppler shift. So this is the lowest mass planet found so far by Keck. The bigger the mass of the planet, the greater the velocity change it'll cause in its parent star. So the most massive planets that are the closest to their parent star are the easiest to detect because they have the largest gravitational influence in the star. We're most interested in things like planets approaching Earth mass. Well, we're interested in all planets, of course, but the holy grail would be to find an Earth mass planet around a nearby star. So this is as close as we've gotten. It's a 22 solar mass planet, and these are the velocities that, when they're phased together, show that this planet has an orbit around the star, and this is the motion induced in the star by the planet. And it, instead of having a 365-day period like the Earth, a year on this planet is only 2.6 days. So there's not much time to achieve your annual goals on this planet. And we're constantly pushing to lower radial velocity accuracy and to get to lower and lower mass planets, and we're monitoring hundreds of planets. This is the work of Jeff Marcy at UC Berkeley and Steve Vogt at UC Santa Cruz and all their colleagues. So there's about 400 planets that have been found by this technique. More than half of them have data from Keck Observatory that's contributed to that. So this is an artist's conception of what that planetary system would look like. I said the planet had a much shorter orbital period, so it's quite close in to that star, and we can get more information than its mass because we're very lucky in the case of this planet. Along our line of sight to this star, the planet's orbit just happens to go right across the face of the star. So when it goes across the face of the star, we can monitor the brightness of the star, and as the planet goes across, the star just gets ever so slightly fainter, on the order of 1% or 0.5%, because it's a darker surface that's replacing the very hot surface on the star, so less energy reaches the Earth. And we can time how long it's getting fainter along the edge, and that gives us the radius of the planet. So we have the mass of the planet from using Newton's laws and the velocities, and we have the radius of the planet. So that gives us a density, and we're able to get a few other clues as to the properties of the planet. So we can start to talk about what the planets are composed of, because density changes dramatically if you make something out of hydrogen and helium gas versus making it out of iron. So we can try different kind of density mixtures of the types of substances that are common in our solar system and see if they're stable and see if they give the right radius. And we believe that this Gliese 436b is made of a small rocky core, and that its quote-unquote mantle is made out of water compressed into solid form, and then it has a thin outer envelope of hydrogen and helium gas. So I think it's thrilling that we've gone from the era where there was a big debate about whether there are planets around other stars to the point where we can talk about what the planets are composed of and really do kind of differential planetology between the 400 planets that we know of, and try to get to the fundamental questions of what causes some solar systems to form many planets, what causes Jupiter mass planets to be where they are in our solar system, yet there's some other solar systems where they're much closer in, and to understand the physics of what's going on in this situation. The thing that limits the Keck telescopes the most is the atmosphere. I told you we're above a lot of it, but still we have to deal with the remainder. So we cope with this with adaptive optics, and Keck was the first large telescope to have an adaptive optics system. So this is a schematic of how an adaptive optics system works to remove the turbulence in the atmosphere, which causes that kind of twinkling or shimmering of the stars. The light comes into the system, and this is a deformable mirror. It can change its shape 2,000 times a second, and this is a wavefront sensor, and it says what optical effects the atmosphere has induced into the images of the star. So you can see the star's jittery from the atmospheric motion. The atmosphere introduces defocus, it introduces astigmatism, coma, and here you have imperfect wavefronts coming in because the atmosphere has distorted them. The wavefront sensor is like going to an optometrist. It says you have this much astigmatism, this much coma, and it rapidly changes the shape of the mirror, this mirror, to exactly counteract the optical aberrations that have been introduced. So it's like getting a new prescription of glasses and that correct the distortions, but you have to do this very fast. The characteristic time in the atmosphere is about 1,000th or a 2,000th of a second on Mauna Kea. So we need to understand every 2,000th of a second what aberrations have been introduced by the atmosphere. We then have to send signals to this deformable mirror that has thousands of actuators on its back and is about the size of, say, a dinner plate. Change the shape of that mirror and then repeat that cycle. So maybe this is an area where we actually have an interest in computer speed that maybe approaches what you do at Google. We need really fast processors for this kind of operation. But the technology is absolutely revolutionary. For the first time, large telescopes on Earth are largely freed of the distortions induced by the atmosphere. This has a lot of other applications as well. You can imagine, just to be able to do better imaging through the atmosphere period. But it's absolutely revolutionary for astronomy. So we get a gain in spatial resolution using the Keck telescopes with adaptive optics on versus adaptive optics off of between 10 and 20, depending on the atmospheric conditions. So typically, on a reasonable night on Mauna Kea, if we're not using adaptive optics, the characteristic size of an image is a half an arc second, so 1/3600th of a degree. In California here, maybe it would be 1.5 arc seconds, 1 arc second. But we can get down to resolutions of 0.15 arc second using adaptive optics on Keck. That's better than the resolution you get in the optical with Hubble Space Telescope. So we're liberated at infrared wavelengths where this works and going into red wavelengths from the expense and complexity and risk of launching telescopes above the Earth's atmosphere. We can build them on Earth, we can build them bigger, we can build them cheaper, they can become more adaptable over their lifetime as new technologies come available, and this is all thanks to adaptive optics. So what do we apply this to? Let me give you a sense of the scientific questions that are really been opened up by adaptive optics. So the center of our galaxy is an area very different from where we live in the galaxy. It's 25,000 light years from Earth. So where the Earth and the Sun are, we're kind of out in the suburbs of the galaxy, and the galactic center is, very much Manhattan or London, take your pick. Just the density is a lot higher there. But astronomers, until they had adaptive optics, weren't really able to study it very well. We're looking through the plane of the galaxy, the plane of the Milky Way to get to the galactic center. There's a lot of absorption by dust, so we have to work in the infrared because astronomical dust very much scatters and obscures optical light, but it's much less of a problem in the infrared. And this is a view of the galactic center determined using the Keck telescopes by a group led by Andrea Ghez. And you can see it gives a beautiful image. This is the inner 1 arc second of the galaxy. So it's a tiny area. Without adaptive optics, this would just be a blur. Now, we always knew this was a very interesting place going way back because one of the brightest radio sources in the galaxy is at the galactic center. But there was very little known about the stars right at the very center of the galaxy until adaptive optics on the Keck telescope started probing this area at very high resolution, led by Andrea's group. And I'm going to show you what the motions of these stars are like with adaptive optics. This is a cartoon. This is the year the data was taken, and it's extrapolated somewhat beyond the present. So each star moves along one of these orbits. And this is the very center of the galaxy. You can see this is a tiny area, only 0.1 arc seconds. Now watch the stars as they go close to the very center on their elliptical orbits. They're accelerated to huge velocities and accelerations as they go close in. You can see them just whipping around there. This will just replay. And this star here they're all extremely interesting that these velocities are this fast. But the star that's most interesting is this one here. It goes very close to the center of our galaxy. It goes within 90 times the distance between the Earth and the Sun of the very center of the galaxy. Now, astronomers have always used the motions of stars and Newton's laws to infer masses. So we use the motions of the planets within the solar system to get the mass of the sun. So we can use those same kind of techniques to use, force equals mass times acceleration and the gravitational attraction law to get what the mass is at the galactic center. So within the orbit, within the closest approach of this star, there is 4 million times the mass of our sun. So imagine that's all in stars. This would be the brightest region of the galaxy, but you don't see anything there. And you really can't put 4 million stars into that, of the sun size, into that kind of region. So this is a black hole. And, a discontinuity in space-time. And we have other evidence with the Keck telescopes that this is a supermassive black hole. We can see flashes of material as they get accelerated and make their final orbit into the black hole. So this is the strongest gravity location in our galaxy. So it's a wonderful laboratory for physics and astronomy. And we didn't even know about it, before the Keck telescopes started looking at this area of the sky with adaptive optics. So it's probably the best place that we have to test the theory of general relativity and the strong gravity limit. It's a wonderful place to understand the properties of black holes. And after this discovery, astronomers started looking at other large galaxies to better understand the demographics of black holes in other galaxies. We can't get this exact kind of data, but we can get more crude data that talks about the motions of these stars from just a spectra of the whole area. And indeed, every respectable sized galaxy has a supermassive black hole in its center. And in fact, the larger the galaxy, the bigger the black hole. So there's galaxies that are much larger than our galaxy, and they have much larger black holes. So it's raised some of the most interesting questions in one of the most interesting questions in astronomy today. How did something that's the size of the galaxy, the whole huge galaxy, for example, our star takes 250 million years to orbit the galaxy, where some of these stars take less than a decade. So we're talking about very, very different scales. How do these two scales know about each other to have those things so correlated? Is this nature or is this nurture? Did you start out with black holes very early in the lifetime of the universe, and they were very important to pulling in a lot of other material that became the galaxy? Or did you have galaxy collisions so often in the early universe that if you started out with a small black hole in at the center of a galaxy, it would just naturally get larger and larger from all the merging activity that happened? So there's a lot of modeling and a lot of other investigations going on to further explore this question. We've had another amazing discovery using adaptive optics just in the last year. In November 2008, this was announced. I was telling you how we now know of 400 extrasolar planets, but we know about them indirectly from looking at the motions of their parent star as the planet's orbit. But that's not a direct detection. And astronomers have wanted to get a direct detection of planets for hundreds of years. And so for the first time in late 2008, this star HR 8799 was imaged with Keck Observatory. And the idea is to use adaptive optics to make the image of the star as small as possible, so that and then try to block it out so that you've removed the source of glare and you can see the planets around it much more accurately. And we succeeded. These are 3 planets around this star. they're big planets. You'd expect that we'd find the biggest ones first, right? They're the easiest to detect. They're 10, 10, and 7 times the mass of Jupiter, and they're in the outer parts of this exoplanetary system. So they're, in terms of the separation between the Earth and the Sun, the Earth-Sun separation, they're 24, 37, and 67 times further than the Earth is from our Sun. This is the work of Christian Marois, Bruce McIntosh, and colleagues. But I think this is the beginning of a revolution in exoplanet astronomy. And I think we live at a very special time. You know, we're living when the first extrasolar planets were found indirectly within the last dozen years. And we're also living at the time when it's the first time we can take images of these. Once you can take images of these, the next logical step is to get spectra. Once you get spectra, you can start to understand what's in their atmospheres. So take this technology and play it forward with much greater capability. Imagine being able to image an Earth mass planet around another star. Let's say you could do that. That would be a huge achievement. And then let's say you could take a spectrum of an Earth mass planet. If you could take a spectrum of our atmosphere, you'd be able to detect that there's quite a bit of oxygen in our atmosphere. You don't have oxygen without some sort of biological processes going on, right? Because it would all oxidize with everything else, form things like rust, etc. So you need something to replenish the oxygen. You could probably detect a spectral feature in our atmosphere. It's called the red edge of chlorophyll. So this is absolutely fundamental step on the way to being able to probe for life in the atmosphere, signs of life in the atmospheres of other planets. I think this is absolutely incredibly exciting. We have another discovery of this sort that was made in 2009 with Keck Observatory. Methane was detected for the first time being released in Mars in the northern summer. This is a map of methane on Mars. With methane concentration is here. So this is incredibly exciting. Let me show you how we do it. You take a spectrum in the near infrared, and there's methane lines in the near infrared. It's kind of tricky because there's methane in the Earth's atmosphere. So again, we make use of this Doppler shift. You find a time when Mars is moving relatively rapidly along the line of sight with respect to Earth. So its spectral features are at a different wavelength than the ones in Earth's atmosphere. This is the work of Mike Mumma from NASA Goddard Space Flight Center and colleagues. And Keck has a very high precision, high resolution near-infrared spectrograph. That's one of the few instruments that has the resolution to be able to detect methane so well. So here's Mars, and this is a slit. The way we get spectra is we have to put a slit, a one-dimensional slit, on an image. So this goes across the disk of Mars, and this is sort of a busy plot, please forgive it. But this shows the density of methane along that disk in the northern summer. And then this shows it in January 2006. So the amount of methane has changed dramatically over that time period. So March 2003 was summer on Mars. And when you go to look at where these emissions of methane are from, they correspond to specific geological regions on Mars that have a lot of cratering and what looks like vents. And so the hypothesis is, since methane gets broken down in Mars' atmosphere, remember Mars doesn't have as protective a layers as in its atmosphere as the Earth does, that methane gets broken down from ultraviolet radiation. Mars doesn't have nearly as much surface gravity as Earth does, so gases can escape. So if you see something in the atmosphere coming and going, it has to be replenished. So the hypothesis is that it's sort of like hydrocarbon seeps on Earth, that there's vents on the surface that go very deep, and when the surface icing thaws in the summer, there's outgassing. And then when you go into the winter period, these vents ice back up, so there's no more outgassing. So there's methane on Mars, it's being replenished, and the really interesting thing is, what's the source of this methane? We know there's geophysical ways to create methane on Earth, and we also know that there's biological ways to create methane. So the big question now is it possible this methane is being created by biology on Mars? We know on Earth that there's microbes that create methane that are subterranean. It's warm enough for them to exist because they're the heated crust from radioactivity. So it's impossible to tell right now whether it's geochemical or biological, but we're really attacking. It has been very exciting to our community, and we're really attacking this with Keck. The first thing we're trying to do is, from those spectra, we can also place limits so far on how much ethane and formaldehyde and other related molecules there are. So we're going to push much harder on that in the time period coming up to try to, because you may be able to trace whether it's geochemical or biological by the relative amount of these other trace materials that are produced. But we haven't used adaptive optics on this yet, and we've modified our adaptive optics system so it'll work at the wavelengths of methane now. So we're going to be able to get 10 to 20 times better resolution on where the methane is being emitted. So we're going to be able to understand where the sources are to an accuracy of about 50 kilometers. So, for us, that's about the size of Hawaii Island, or even smaller. So if you can localize it to an area like that, NASA could put a spacecraft into there someday, and NASA is incredibly interested in this. So stay tuned for what's the verdict on whether the methane on Mars is biological or geochemical. It would be an amazing discovery if there's really biological life on Mars, and it would really, I think, change the way that we envision ourselves here on Earth. So what about the future? This is an image of for our adaptive optics system with Keck. We actually launch a laser into the sky. Originally, what we'd have to do is do adaptive optics near bright stars, and that's what fed the wavefront sensor. But bright stars aren't that common. We want and need to be able to use adaptive optics everywhere. So we developed a laser technology that excites the sodium atoms in the very upper atmosphere, and that creates an artificial star. So we can create an artificial beacon near any place that we want to do adaptive optics on the sky. And so I've told, this is a recent technical highlight and enabled a lot. And I'd like to talk a little bit about the future in astronomy and at the observatory. We're continuing to push on adaptive optics. The current systems only use one laser guide star, and we're designing a new system that uses multiple laser guide stars, perhaps 9, so that we can do tomography of the turbulence and the whole volume of atmosphere above the telescope. No one's done that yet, but that will effectively give as high resolution images as you can possibly get out of a 10-meter telescope, and it'll allow the full attainment of the Keck telescopes. It's going to allow a lot of new kinds of science, like watching planetary systems in formation. This is a simulation of a solar system forming and how we could see it in its early days. This is a simulation of the galactic center. This is Keck's current AO system, and you can see it's kind of blobby in the center, but we can break it better into individual stars to understand those orbits with a more sophisticated adaptive optics system. So we're working very hard on that right now, and that's our #1 technical priority. So in wrapping up, what does the future look like for ground-based astronomy and Keck Observatory? The observatory's been really productive in terms of the scientific papers and scientific results. I hope I've given you a taste of that with the work on understanding exoplanets and with the amazing discoveries at the Galactic Center. We'll continue to lead. The observatory is very dynamic. We're extremely committed to bringing on new technologies and new instrumentation and adaptive optic systems to allow the observatory to do more each year and discover more. And some of you may have heard that we're coming to the time period in astronomy where people are starting to think about mirrors that are even bigger than 10 meters. So what are we going to do with our 10 meter in that era? One way we'll shift is we'll enable very large observing programs. You have to work really, really hard right now and have an incredibly bright idea to get a few nights in the telescope. But we'll start to open it up so for the people with the best ideas will maybe be able to get a month of telescope time and just create incredible data sets that we can't even imagine today. There's some very large imaging surveys. The Large Synoptic Survey Telescope and Pan-STARRS are two projects that are envisioned coming online. And I understand maybe there's some Google involvement in the Large Synoptic Survey Telescope. But these systems will be able to map the sky with a time scale of a few nights. So you can map the entire sky in a few nights, then go back and map it again and see what's changing. So look for stars that are varying, flashes in the night that we wouldn't even be sensitive to right now. So that'll be these amazing imaging data sets. We really want to optimize Keck to follow up on those spectroscopically, because spectra really give you so much more information. It really gets much more at the physics of what's going on. So we're going to be, as these imaging surveys come online, we're going to be optimizing our instrumentation and our observing procedures to really be able to leverage them really well and to learn a lot more about time-sensitive phenomena, monitor time-sensitive phenomena that have been found with these surveys spectroscopically. These very large telescopes will be very expensive and very project management intensive, so they won't be able to take a lot of risk, but will remain small and nimble. So I see ours moving to higher risk, higher reward kind of instrumentation and adaptive optics, and being a real proving ground for those kind of innovative instrumentation concepts that you can't afford to take the risk for on the large telescopes, the very large telescopes, but that will migrate there eventually. But I have a prediction, and that's that with the adaptive optics now fully developed, our community really using the telescopes and partnering with us so well that the next 10 years before these extremely large telescopes come online will be the most productive in the observatory's lifetime, and that'll be the real legacy discoveries that keep us in the astronomy books that are published 100 years from now. So I want to thank you all for coming today, and thank you for your interest in astronomy. And if any of you are out in Hawaii ever, well, we'd love to show you the observatory. And it would be great to do more with Google and all you Googlers. Thank you.
So we have time for a few questions. I have a mic over here if you're able to get in range.
I have a question about the adaptive optics mirror.
Yes.
That changes so quickly. What kind of material do you use to do that? What's the mirror made of? I'm
trying to think of the exact substance, but it's a rubbery. I'll get real technical. It's a rubbery kind of substance that you can place an aluminum coating over. So it's a very flexible ceramic, and then there's piezoelectric actuators behind it that do the changes. We're moving to new technologies there with micro machine devices. So that's the MEMS are really the future in this area in terms of being able to get really high actuator count.
Right, well, I was wondering if you could talk more about the outreach that Keck does to, like talks like this are awesome, but how do you diversify this knowledge through the community?
Yeah, great question. We're really blessed that so many people are interested in astronomy, so it makes outreach really easier in astronomy, I think, than in a lot of fields. So we have monthly lectures at our headquarters where we have mostly astronomers are doing scientific research, give the lecture. They're all podcasts. So if you go to our observatory website, keckobservatory.org, you can get at those podcasts. We sometimes have lectures about new technical things we're doing, but it's mostly science results. We publish an e-magazine that comes out approximately quarterly called Cosmic Matters. We have astronomers and engineers who go into the classrooms in Hawaii Island and communicate with the school children about the excitement of astronomy. And we participate in the visitor center on Mauna Kea, where people who are visiting Hawaii or locals can go and look at the stars at night on this amazing dark site. I'm sure there's more, but that's what comes to mind immediately.
Can you tell us a little bit about how Keck can be used to observe or indirectly imply dark matter?
Yes, dark matter is one of the most exciting areas in astronomy, I think. And let me just introduce dark matter with a word. Sometimes I create confusion by showing that pie plot of the dark energy and the dark matter. But the dark matter is where we just see the gravitational signs of matter, but we can't explain it with stars or planets or other baryonic matter. So I'd say the laboratory we're doing the most on dark matter in right now is the Milky Way has a number of small dwarf satellites. So these are galaxies that have, on the order of 1 million solar masses, 1 million to 10 million. And we can infer that from the motions of the stars in the galaxy. It turns out that these are some of the dark matter richest objects that are known in the universe. And so we're really probing the numbers of these, their dark matter content, how the dark matter is distributed within them, because they give us the best information about the clustering length of the dark matter. Different forms of dark matter will cluster on different scales. And by having dark matter cluster on a rather small physical scale, it rules out a number of different types of dark matter, different types of particles that could make up the dark matter. And we're very much involved in exploring with these dwarf galaxies the theory of large galaxy formation, the hierarchical structure formation theory that says there was a lot of aggregation of dark matter into these dwarf galaxy-sized chunks early in the universe, and that big galaxies formed by aggregating or merging, these small dark matter clumps. So we're testing that theory in great depth around the Milky Way and around M31.
Yeah, the animation of the Galactic Center was really very fascinating. I believe I've read that in recent weeks and months, a couple of teams I think they've observed a halo around the Galactic Center in the radio.
Yes, in the submillimeter and radio.
The gamma ray range. And the more courageous astronomers are speculating, looking over their shoulders, gee, could this be the dark matter particles colliding and forming electron-positron clouds? Anyway, it's really early on, but is this the kind of thing that infrared astronomy might be able to help with?
It's a great question. I heard
you're seeing it at gamma rays and you're seeing it at microwaves.
It seems very sensible that we should go and look for this. I have to admit, I heard the discussion at radio wavelengths, and I simply haven't followed up with our experts to understand what we're doing about it. So I'll get on that when I get home.
Hi. So when you're doing the imaging, you're probably feeding the light straight into a spectrometer, right?
Yes.
So when you do CCDs, you have to do a lot of calibration, like flat frames and bias and all that. Do you have to do the same with spectral analysis, or?
Absolutely. And we call it removing the instrumental signature.
And so are you doing that in real time? Because usually what I do is, I capture light and then I capture the dark frames. So I'm wondering how you do it in real time and stack it in real time.
I think we could improve how we're doing, but what we typically do is we take a lot of the calibration data in the afternoon, the biases, and then we initially start with creating the flats by the data that have been taken so far during the night, or flats we've been able to take during the afternoon. So we try to, over the night, do quick look reduction, but often the final data reduction product has to wait until the next day when we can look at all of the data from the night, particularly if it's very, very faint work and we need to make, say, a super flat from all the objects during the night with the stars and galaxies removed.
So one additional question I had is the adaptive optics. Right now, there are some products available for a couple of $1,000 for amateurs, right? Which is based on refraction and lens movement, adaptive optics elements, right? Do you know anything about them, or?
I'm afraid I don't. All of the products that we have are kind of custom made for the. I mean, we buy the deformable mirrors commercially. And we're trying to get a source of commercial lasers that's reliable, but I don't know almost anything about the off-the-shelf products for amateurs. I think it's really exciting, you know, that could be applied to other telescopes, kind of the democratization of astronomy with people being able to buy their own telescopes and their own CCD cameras has been wonderful. So I see the, you know, availability of adaptive optics systems to, you know, others than really major observatories, just a continuing of this democratization, and really cool.
So one final question, the optics itself, it's RC design, I believe, right? The Keck, the 10 meter?
Yes.
Okay.
Right, I think we have time for one more question. So.
Hey, thanks. That was inspirational. You mentioned one thing early on, which I'm curious about. What did you look at on the moon?
Oh, yes. You know, I was hoping that the data analysis in this project would be done because earlier this fall, we observed a NASA experiment on the moon. And let me back up just one step. We don't usually observe the moon, so NASA had to allocate a special observing run where we could just make sure we could track and guide on the moon, because it's so, you know, it's such an unusual thing to observe with a large telescope. So NASA crashed 2 rockets into the moon with the idea that it would bring up some of the subterranean soil. It's called the L-Cross mission. And Keck and a number of observatories, but I think we got some of the best data, looked at the material right after this impact with an infrared spectrograph tuned to the wavelength region where water vapor would be detected very well. And the astronomers who took this data, it's embargoed right now, and they're working really hard on it to see if water vapor was detected with Keck and that same spectrograph that determined the methane, called the near-spec spectrograph. And the NASA's long-range interest in this beyond science is if they ever establish lunar bases, you know, could they have some apparatus that just went a little into the soil and got the water. So we're all eagerly awaiting the result, and we'll disperse it through our networks. By the way, I'd encourage you all to sign up on our website to get news from the observatory when we do have media releases about things like determining whether there's water on the moon.
Well, Taft and our friends from Keck, thank you very much for coming. This was an amazing talk. Thank you.
Thank you so much.